All right, let's give it a go. So you have the star and the triangle, and you're trying to do a combination of the star and the triangle, and you have to figure out what does it look like. A combination of the star and the triangle. And people said, 12 people said A, 2 people said B. We have 2/3 of the star and 1/3 of the triangle. So I think everybody realizes it's going to be somewhere between star and triangle. There's a funny special name given to this kind of combination. Does anyone know what this kind of combination is called? Yeah. It's true, it is a linear combination. So anytime you do anything of times this plus anything times that, it's always a linear combination. And a linear combination will be somewhere in the span, but this is a special type of linear combination. Yeah.
Affine.
What is it?
Affine combination.
Affine. Usually to me, affine is like linear plus you're allowed to add on like a constant. So I guess it's technically affine, but that's not what I'm going for. No, that's the same as linear. It's a special C word.
Oh, it's not linear.
And it has to do with the fact that these 2/3 plus 1/3 sums to 1. 2/3 and 1/3 sum to 1. Does anyone remember what this thing is called? Here, let's do a quick little Desmos, since you guys haven't seen this before. Let's do a Desmos. So let's have some points. Let's make x be 2, 1, and let's make okay, let's call them A and B. 3, 2. Okay, let's see. I guess 1, 3. Okay, there we go. We'll call that A and B. And then if we do t times A, actually let's make it a slider. Let's call it S. S times A plus 1 minus S times B. And then we're gonna add a little slider for S. So now it's some new point. When S equals 1, let's see if we can make this a bit bigger by zooming in. Okay. Okay, so when S equals 1, what is this combination? Well, it's just 1 times A, so that's exactly A. When S equals 0, that's the other side. But what happens when it's in between? Oh, look at this. So if I play it, let's make it go from 0 to 1, and let's have it animate back and forth. What is S times A plus 1 minus S times B doing? So this is the special kind of thing. When the coefficients sum to 1, yeah, somebody said it. What was the word?
Convex.
Convex. This is a convex combination. So when your coefficients sum to 1, then it's a convex combination. I guess they also need to be greater than 0. If you start doing negative stuff, you're going to keep going past the other way. So click, come back, please. If you go past 1, what happens if we go past 1? Let's see. If you go past 1, whoa, you went too far. So if you go past 1, then 1 minus S is negative. Then you're past the thing. But a convex combination is when the coefficients are between 0 and 1. And that is what we were doing over here. Convex combinations. That is the little thing. And indeed, in this case, the answer is A. So very good job to everyone who got A. And the reason it's more towards star than towards triangle. So it's a convex combination that's somewhere on the line between star and triangle. And it's more towards star because it's 2/3 of the way towards star and 1/3 of the way towards triangle. So actually, if you took this line segment and you cut it into pieces, this is 1/3 and this is 2/3. It's 2/3 of the way towards star. Okay, that's a convex combination. Why do we care about convex combinations? Because we are doing averages of things, and averages are a special type of convex combination. So let's see if we can get our notes open. Okay, and I guess I need to close the little side tab, and I'm gonna try drawing over here. Okay, so does this work? It does not work. That's a problem. Okay. All right, we're gonna switch to the blackboard because I'm having some problems. Okay. So we're doing the convex combination. And so in the convex combination, the coefficients are between 0 and 1 and they sum to 1. Some people also use lambda. Lambda times A plus 1 minus lambda times B. Or yeah, let's do it this way. Lambda A plus lambda B times B, where lambda A, lambda B, they're always between 0 and 1 and they sum to 1. Lambda A plus lambda B equals 1. Okay. Okay, and we care about this because we're doing averages. So we have some sequence of data. We have these outcomes x1, x2, x3, dot, 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 all the way up to xn. And we want to find the average. And this is under the heading of Monte Carlo methods that we started right before the snow day, Monte Carlo methods. And in a Monte Carlo method, we're working with samples and trying to use the samples to figure stuff out. And the one thing we're especially interested in is their average. Mu n is 1 over n times x1 plus 1 over n times x2 plus dot, 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 plus 1 over n times xn. So it's the average of the xn's. And this is a convex combination, so all of these coefficients of size 1 over n, they are all between 0 and 1, and they add up to 1. So this is a convex combination of x1 to xn. So if you're going to draw a little number line here and think of the points x1, x2, x3, they're on some number line, like they drop out of the sky and fall towards some number line. We're doing a convex combination. We're figuring out the average, which is somewhere in the middle. Mu n is the average of the points. Okay. Why do we have to think about these convex combination things? Like, why am I making things complicated? Well, the reason is I want to justify this formula that mu n plus 1 is, I'm going to write it like this, n over n plus 1 times mu n plus 1 over n times xn plus 1. So this is what we finished off with at the very end of our previous class, saying that you could figure out the average of n plus 1 points by knowing the average of the first n points and what is the last thing. So this is sort of a way to do it. And you'll notice that this is also a convex combination. So to get the average of the first n plus 1 points, you do a convex combination of where it was before, adding on a little bit for the next point you get. Okay, you guys with me so far? Any questions or comments? Okay, so let's justify why is this thing true. And I think there is a nice sort of picture-proof way to do it. So if mu n has a coefficient of 1 over n of all these things, mu n plus 1 is supposed to have a coefficient of 1 over n plus 1 times all these things. Yes?
If that's the case, shouldn't the x n plus 1 come n plus 1?
Ah, very good, yes. Good catch, yes. So it depends if you write mu n plus 1 or if you write mu n in terms of mu n minus 1. But yeah, you're absolutely right. That way they sum to 1 and we're happy. Okay. Let's see, 1 over n plus 1 times xn plus 1 over n plus 1 times xn plus 1. So what do we have to do to convert mu n into mu n plus 1? Well, we have to change all the coefficients of 1 over n that were there before. We have to change them into 1 over n plus 1s. And then we have to tack on this new thing. And this multiplication by n over n plus 1, it exactly converts a coefficient of 1 over n into a coefficient of 1 over n plus 1. So if I was going to write n over n plus 1 times mu n, that would be n over n plus 1 times 1 over n times x1 plus plus n over n plus 1 times 1 over n times xn. And then we have the nice cancellation. The n's cancel, right? So 1 over n plus 1 times x1, it exactly becomes that. And then what do you have to do? You have to add on 1 over n plus 1 times xn plus 1. That's exactly what we did. So this is a little mini proof justifying this formula, which last class I called it the online average formula. And the reason it's online is because you get to do the average bit by bit. You don't have to wait until the end and then add up all your numbers. You sort of go, as you get a new number, you update the average, and you keep going and going and going. Okay, this is kind of a leftover from the previous class. I think I might have even said you guys should do it, but I did it just now. Questions or comments about this formula? Okay, yeah.
So in the last class, you had a slightly different version of it, where was the mean? Was the new mean was the mean plus the sample minus the mean divided by n.
Okay, yeah, this is great. So another way to rewrite this, if you just rearrange this formula from the way I have written it, if you rearrange it, so you got n over n plus 1 times mu n. Well, we could write n over n plus 1 as you start with 1 and you subtract a 1 over n plus 1. So this is one thing. And now you see that there's a 1 over n plus 1 both in front of the mean and the xn plus 1. So an equivalent, totally equivalent way to write it. Mu n plus 1, it's mu n, that's the 1 times the mu n. And then you have the 1 over n plus 1 stuff, plus 1 over n plus 1 times what? Times xn minus mu n. Okay. And that is probably what I wrote last time. And this one is very suggestive as well. It's saying the new average is the old average plus updated a little bit. And there's this little coefficient here of 1 over n plus 1 that is telling you how much to update. And the xn minus the mu n is the direction you update. So if xn is higher than mu n, then you're going to move it up a little bit. If xn is lower than mu n, then you're going to move it down a little bit. And you can kind of visualize this with pictures. If you have all your points and you get a new point, right? You have a new point, xn plus 1, it's like way bigger than all the other points. Then it pulls the average towards the xn plus 1. If xn plus 1 is way below all the points, then it's going to pull the average down. And the amount of weight it has is sort of 1 over n plus 1. The more points you have, the less weight each individual point has. All right. And the reason this formula is important, we're going to have a version of this called the constant alpha averaging version. Alpha averaging version, which is the same kind of formula where you do mu n plus 1 equals mu n, but you replace 1 over n plus 1 with some alpha in 0, 1. And so here, alpha is a parameter, in 0, 1. Okay. And once again, you can write this as a convex combination. It's 1 over alpha times mu n plus alpha times xn. So it's still a convex combination of the previous guys. And because mu n is also a convex combination of the previous guys, you have a convex combination of a convex combination. Mu n plus 1 will still be a convex combination of the xn's. So let's try to guess what it is. Let's give this thing a name so we don't confuse it with the n's. Let's call it mu alpha, the constant alpha average. But alpha is everywhere. Okay, and now we're gonna let's ask ourselves what the coefficients are. So mu alpha n, I claim it's some combination of x1, x2 plus dot 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 all the way up to plus something times xn. The xn part I can tell you what it is. I guess maybe this should be xn plus 1 to keep people happy. Okay, and then I'll put a plus 1 here as well. Plus 1 and plus 1. And so this coefficient, this one's alpha. What are the coefficients beforehand? Well, on xn, it's 1 minus alpha times alpha. And it gets the 1 minus alpha from this step, and it gets the alpha from the previous step. And the one on before that is going to be, so if I look at xn minus 1, it's going to be 1 minus alpha times alpha squared times xn. And that's because, nope, it's going to be 1 minus alpha squared. Okay, there we go. So every time you sort of go back, you're multiplying the previous thing by 1 minus alpha. And so the thing 2 times ago got multiplied by 1 minus alpha twice. So it's this kind of formula. Alpha, 1 minus alpha times alpha, 1 minus alpha squared times alpha, dot, dot, dot. Going backwards, it's 1 minus alpha to the k times alpha times x to the n minus n plus 1 minus k, I guess, is the general term. Yeah.
I was gonna say when there's limits of that.
I mean, it's very possible I made a mistake somewhere, but I think that's the right thing. So, okay, so this formula goes on forever. It should be a sum over k. So what is the point? It's a convex combination of the points, but you're weighting them all differently. So for example, if alpha equals 0.1, then everybody gets a weight of at most 1/10, with the latest guy getting a weight of 1/10. But then the further back you go, you're discounted by 90% every time. So xn gets 0.9, xn minus 1 gets 0.9 squared, so like 0.8. Xn minus 2 gets 0.9 cubed. So the further back in time you go, the less it is weighted. So you're kind of weighting the future more. These are the current estimates weighted more. And the things back in time are weighted less. Weighted less. Okay. So the things are not all equal, like in the traditional average. They are sort of made in this funny way where the most recent things are weighted the most and the things in the past are weighted the least. This might seem very strange, but you will see why we want to use it later. So I thought I would bring it up now while we're talking about convex combinations. Probably right now you're thinking, this is crazy, why would anybody do this? But you will see why soon. All right, any questions or comments about that? Okay, so now we are going to take all this, like, so far we've done some kind of like theoretical stuff about averages in general, right? Our Monte Carlo methods, we did that thing with the circle, we did this online stuff. And now we're gonna try to apply these Monte Carlo methods, these averages, to our problems. And I came up with a fun example that I want to do today. We're trying to do it with Monte Carlo, and the thing we're gonna estimate, remember a Monte Carlo method estimates something non-random by using random samples. And the thing we're going to estimate is the value function v from the first half of the course. So the first half of the course, we found the value function v of s, which was the expected value of the total return, or let's say the total rewards given you're in state s. S0 equals lowercase s. So this is already, it's an expected value, so you could try to estimate it by a Monte Carlo method. That means trying to run a bunch of simulations to see how much reward you get, and then writing down the function v as that kind of average. And the example I came up with to try to do this in is a game that's very similar to Pig. Let's see if I can exit out of this. Okay, it's a game very similar to Pig called Zombie Dice. So here is the game Zombie Dice that we're going to be doing. The tagline of the game is "Eat brains, don't get shotgunned." So unlike most zombie-themed things where you fight the zombies, in this game you are the zombies. Okay, so how does this game work? Let's get them out. Hopefully they're in my backpack, so we can do them. So here are the zombie dice. Let's see if I can get this going as well. That'll be fun. Doc cam.
Can you say brains with the most feeling? No.
Okay, so these are what the dice look like, if this will turn on. Which will it? I guess we're going to find out.
Wait, are you first player?
I'm the first player, yes, I guess. Have you played this before?
No, but if it's a first player, it has to say brains the most feeling. So.
Oh, I see, yes. Yeah. Right. Well, as usual, we are going to play the one-player version first. Okay, let's see if I can get this to turn on, though. This might be a problem. Hello? There's your problem. Okay, so in Zombie Dice, you roll these beautiful dice, and they come in this tube, and you roll 3 at a time. So you get 3 of them, and you roll them, and they look like this. So here I got 2 brains, and I also got a shotgun. So 2 brains and a shotgun. You're the zombie, so you're trying to collect the brains and not get shotgunned. So the shotguns sort of count against you, and the brains are what you're trying to score with. That's what the dice look like. You're going to roll sort of 3 at a time. Let's roll 3 more. They look like this. Here I got shotgun twice, even though I collected 1 brain. And there's a rule in Zombie Dice: if you get shotgun 3 times, you die. So I went bust. I should have stopped rolling, or earlier, if I had stopped rolling after my first round, just like in Pig, I could have banked those 2 brains and done my best to get 2 points there. But I was too greedy, and I went over the greed limit, and that is why I am dead. So let's go back to the rules quickly.
What happens when it's a red shotgun?
Yes, I will tell you about the colors in 1 second. Yes, this is one of the exciting things that makes it exciting. So on your turn, shake the cup, take 3 dice from it without looking, and roll them. The easiest, each one is a human victim. So every dice represents a person. The red dice are the toughest, the green dice are the easiest, and the yellow are medium tough. And so every dice will have brains, shotgun, or footprints. Brains are like you ate the person's brain. Shotgun is like the person fought back and shot you, and footprints is like they ran away. And the people who are red are the toughest, so they have more shotguns and less brains. And green people have more brains and less shotguns, so they're easier. And yellow are somewhere in between. So brain, you ate the victim's brain. Set your brain dice to your left. This is just like in Pig, right? You roll points. When you get points, you get to collect the points. Shotgun, he fought back, set your shotgun dice to your right. Footprints, your victim escaped. Keep your feet dice in front of you. If you choose to roll again, you will re-roll the same dice again. If you roll 3 shotguns, you're out. Otherwise, you can choose to stop or score. So just like in Pig, this is a game where the action you're taking at any given time is roll again or stop. Roll or stop. If you decide to stop, you're going to score 1 point for every brain you have. Great. If you choose to roll again, then you keep rolling and you keep adding collections to your brains until either you stop or you collect 3 shotguns and lose. So very similar to Pig, but it's got cool, colorful dice and things like that. Should remind you a lot of Pig. Maybe that was a long time ago, but it's like a fancy Pig. Any questions or comments about the zombie dice? Yeah.
Are the dice you select going to be random, like color type? Or
It says right here.
Oh.
You what does it say? On your turn, shake the cup and take 3 dice from the cup.
Oh, okay.
So you shake the cup and then you take 3. Yes. Okay. So let's do a round together. You guys can tell me what to do. We can sort of vote on what we think we should do, and then we will use our Monte Carlo methods to try to figure out the actual correct answer. Okay. So here we go. I'm going to take 3 dice. I guess at first you always want to roll. I think actually the way I set this up on the computer, you have a choice. When we start with nothing, should we roll again or not? What do you guys think? Bank, yeah. No, don't bank. We're rolling again. So very first round, we roll again. Hey, we got 3 brains. Amazing. Beautiful, beautiful thing. What do you guys think? Should we roll again or should we bank our three brains? Put your hand up for roll again. Okay, everybody wants to roll again wisely.
So the brains are worth the same no matter the color.
The brains are the points, and they are worth the same no matter the color. Correct. Yes. Yes, very good question. All right, roll again. All right, 2 shotguns and 1 more brain. So we're up to 2 shotguns and a brain. So we can choose roll again or stop. Who thinks we should roll again? Who thinks we should stop? Everybody thinks we should stop, so let's stop. We stop when we collect 4 brains. Very good. Just for fun, as they say on the game shows. Let's see what would have happened if we had rolled again. We would have died, so very good. We exited at the right moment, and we took our 4 brains and went laughing to the bank. Okay, so that's Zombie Dice. Very lovely game, and we're going to solve it just like we've been solving all sorts of games in this course. And the question is, in Zombie Dice, so as with Pig, we're going to start with you're supposed to play 2 players and play first to 13 points or whatever, but we're going to start with the 1 player, 1 round version, just like we did. So you play Zombie Dice. You can't see this because I don't have the setting right. Let me change this out. Okay, so we're going to play the 1 player, 1 round version where you saw the rules. At the end of the round, you get $1 per brain, and your goal is to maximize your average. So there's no weirdness with like trying to get to a certain amount or something. You just want to get as many brains as possible. And I have 2 true or false questions. True or false, you can model Zombie Dice as a Markov decision process where the state is 2 numbers, the number of brains you've seen so far and the number of shotguns collected so far. So you saw me collecting those to the left and to the right over here. And then true or false, we can solve this the same way we can with Pig, just by the rules of the game, so we can solve it. So those are 2 true or false questions for you. Yeah, quick.
Is it round until it just goes keep rolling until you decide to stop?
It goes until either you decide to stop or you get shot 3 times.
Okay.
Yeah, that's right. Okay, I'll let you guys think about this for a minute, and we'll see how you guys do. Okay. Unfortunately, my timer is also broken today, so I'll jump up and down and yell beep 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 in a minute. Okay. Actually, yeah, we can use this. We'll say let's stop here. When this gets to 3 minutes, we'll stop. So you have 1.5 minutes. That thing's counting up. Okay, it's at 3 minutes. I'm gonna close it in 1 second. Get in your final answers here if you haven't yet. Let's see what people said. Okay, let's see. Reveal the counts. So true or false? 10 people said true. 5 people said false. Number of brains collected and number of shotguns. That was for the first one. Can we do it as true or false? In the second part, can we solve it like we did for pig using the rules? Very close. This one was false 8 and 7 true. So extremely close. Let's do a revote and see what you guys think. So talk to your neighbors and figure out what do you think is going on now that you've seen what the sort of majority thinks. Okay, I'm going to reopen it in 1 second.
Yeah, we're gonna yeah, it's really sad. It's a little bit. It's really good.
No, but in our
Oh, you know what? That's not fun.
we'll see.
Because, I don't think the doctor should get the organization. Is that what it is?
No, you're right. But I don't think it's necessary. Like, if it's a finite dice, if it's a finite dice though, the color of the green doesn't matter. It's just a random percent. The probability will change.
Okay, let's stop there and let's see what you guys said in the revote. Submission with the labels displayed. Okay. Oh, this is interesting. Before, in the first one, you guys were mostly in true. It was 2/3 true and 1/3 false. Now it's the other way around. That's interesting. Okay. The one I wanted you to vote on was this one. Okay, this one. Ooh, this one's still very flip. So in the one where there was a majority, you guys flipped, which was actually quite wise because you got it right. So if you flipped here, before you guys were wrong. So it is false. The number of brains and the number of shotguns is not a state that would make this a Markov decision process. Does anyone know why the answer is false here? Or can anybody explain why? So you guys got it right. It is the correct answer is false. Why is the answer false? Why did you guys switch if you have don't know why? Yeah.
Well, I think there's more information than just the two numbers, the colors.
Exactly. So there's the colors. Somehow by doing the just the number, I'm deleting all the information with the colors. If I included the colors, it would still turn out it's not a Markov decision process. So if it was the number of brains collected, the number of shotguns collected, and the colors of the number of the brains you've collected and the shotguns, so exactly like what you see when you look here, that's still not a Markov decision process. Is that what I'm saying? Yeah, okay. So there's one other thing, which is you sort of have to keep track of which dice have come out of the box already. So if you've seen a green one already, I guess they can't go anywhere. So you can always know which ones are there. But you got to keep track of which ones have come out already, or it's not a Markov chain, right? So if it depends on what has happened, And that will depend on the colors that you've seen. So if you've seen a bunch of reds already, then there's all the reds are gone, and in the future you'll get only greens. So it violates the Markov property. If you just know the number of brains, it's not enough information. Yeah?
Since we're not always rolling, since there's a certain number of dice, does that affect it at all? Because if we run out of dice, then we have to stop rolling.
That's true. Actually, there's a little thing in the rules that says if you run out of dice, you put them back in, and then you keep rolling. So but you still collect. You still collect. So the brains you collect, you write down how many you have, and you put them in here. Actually, I can show you here. Yeah, brains? Question mark. If you don't have 3 dice left in the cup, make a note of how many brains you have and put them in the cup. Then continue. Okay. So yeah, I guess because of this one, the thing I was saying earlier is true. If you know the colors of the things, you also have to know the colors of all the things you've seen so far and the colors you've seen before. It's a little bit like if you're playing a game with a deck of cards, you have to keep track of which cards have gone by, because those cards are definitely not in the deck anymore and will change the probabilities. So something like blackjack, if you know the cards in front of you, but you forgot all the cards that went by, it's not a Markov process anymore. You need to keep track of all the information that affects the future probabilities, and the colors definitely do that. So, okay, very good. You guys figured that one out. In the other one, I suppose people were a little bit split. So let me see if I can hide the correct answer. Okay, in the other one, people were split. 8 people in false and 7 people in true. Does someone from either camp want to say? Yeah.
I guess your explanation for the state space kind of got rid of it, but that was my logic anyways. I think it's false because the PDF doesn't give us the probabilities from the dice, so we don't actually know the transition probabilities between the states.
Yeah. Okay. That's one. So one problem is it's definitely not going to work with this state space. But if you put in the colors, would it then work? So in your point, would.
Yeah. I suppose in that case, anyways, because even if we include the color, we don't know what the probability of any particular color dice from any particular number is from the BX. So that's.
Yes. Okay. So very good. So the correct answer is indeed false. So it's false, false, were the two things. Congratulations if you said false, false. And you'll notice that it never tells you, it says red is harder, but it doesn't say red has so many brains and has so many shotguns and so on. Let's pretend I also tell you, we can examine one of these dice. Let's get one of each color. So I'll tell you, we can look at the dice individually, and I can tell you that a red has 3 shotguns, 2 footprints, and 1 brain. Green has 3 brains, 1 shotgun, and 2 feet. And the yellow has 2 of each. So 2, 2, 2. 2 shotguns, 2 brains, and 2 feet. So now that you know the red, the green, and the yellow, now can you solve it like you did before? Yeah.
I think no, because how you got there matters, so you can't use the same problem.
Yeah, so when you say how you got there, what do you mean?
How, what your number of colors for the brains and the shotgun.
Yeah, that's right. So there's one extra piece of information, which is the number, what's actually in here. How many dice are in here, how many greens are there, how many reds are there, how many yellows are there. So in addition to counting up the individual sides, you also have to go through the box and do everything. And if you did all that, then you would finally be able to do it like we did in a previous class. So you'd have to if you wanted to do the algorithm from before the break on this zombie dice game, you have to count up all the individual things over here. You have to make your state space super big because you remember it's the number of greens and the number of reds and the number of yellows that also matters. So that's very hard to write down, right? It's not just one number, it's 3 numbers, the reds, the yellows, and the greens, plus these 2 numbers. So now you're up to 5 dimensions. You got to count all this up, and you got to keep track of how many are gone and so on. So it's really quite annoying if you really want to do it like we did before the break. But what we're going to do is we're going to learn how to do this problem the Monte Carlo way, which is just by simulating it. So imagine you could only play the game and you could observe what's going on. You can still use runs of the game to sort of learn the value function v and do all the things we did before without knowing the rules of the game. And in fact, we're going to use this as our state. And I said that it's not a Markov decision process because it's something very slightly different called a partially observed Markov decision process, also known as a pomme de peu. Let me write it down. So, a partially observed Markov decision decision process. Okay, and so this is a POMDP, a POMDP. And what it is, there is a Markov decision process. Like if I really did all the work and wrote everything down, including the colors and what's in the cup, then it would be a Markov decision process. But by only writing down the brains and the shotguns, that I'm only seeing part of it. And when you only see part of it, the parts that you don't see, they can create a memory between what happened in the past and what happened in the future. And so it's not, strictly speaking, a Markov chain. So the example is zombie dice observing only number of brains and number of shotguns. So if you just count the number, it's not Markov because you threw out the colors, but it is a partially observed. This is part of the Markov state, but not the entire thing. The reason these are useful in practice is, one, we can simplify things quite a lot. So when we run the code, we're only going to keep track of these two things. It's a lot easier to manage, and maybe like your final strategy that you come up with will only depend on this anyway. Another example is like anytime you do something in real life, there's always things in the real environment that you can't handle, that you don't know about, right? So if you were trying to learn something about a robot moving around a room, like a Roomba, the Roomba, of course, cannot know everything in the room, and so it's not Markov, but it is a partially observed Markov decision process. You can observe whatever the sensors of your robot can pick up. So another example is a robot. A robot who is not omnipotent, all right? So they don't know everything, but they know some stuff. There you go. Okay. So it's a partially observed Markov decision process, and we're sort of taking all the possible states that could correspond to a number of brains and number of shotguns and treating them as one state. And we're hoping that things will work out. You can get very specialized with this stuff, but for us, we're just gonna be aware of it and kind of pretend that this is a state, even though it really, strictly speaking, isn't. Okay, questions about the partially observed? Yeah.
Do you still want colors for the partially observed?
So what I'm saying is, I'm using this, and it's not a true Markov decision process. This is the part that I'm partially observing. I suppose there's more stuff, and in this case, the more stuff is the colors. But in a partially observed one, you get to only observe these
Still be
things.
partially observed even with colors?
Yeah, so what I'm saying is just the brains and the shotguns on their own, they're the observed part of the whole thing. Yeah, I guess it depends how you want to write it down. Normally, you just focus on the stuff that you can see. So just like the robot, you would only focus on what, like the robot would decide what to do based on its sensors and not like worry about, the other things in the space. Yeah. Okay. Great. Yeah, that's a good way to think about it. We're only going to think about the brains and shotguns. Okay, so what I did is I wrote us a little bit of a simulator here. So here's the simulator. Ooh, let's see if I can make it white instead of dark mode. How do I probably go to settings, and I want theme light. Okay, there we go. Save. Okay. Let's make it bigger. This simulation bit, I went through and I wrote a little simulator that simulates the dice. So I had to count up all the dice in here. It turns out there's 3 of one type, 4 of another type, 6 of another type, and these are the sides. So I did this stuff, but we're gonna pretend we don't know any of this stuff. We can just run this simulator, and when you run the simulator, you get a string of outputs like this. So the simulator says, in this situation, it came out shotgun, shotgun, feet, and then in the next roll it was brain, feet, shotgun, brain, feet, brain, and then in the next roll it was shotgun, brain, brain. You'll notice if you were rolling up to here, you'd be dead already, but the simulator just rolls the dice until we're out of dice. So it goes all the way up to here, and we're going to use these simulations to learn the value function v. So that's the simulator, and we're just going to use the simulator to try to learn what we can. Okay, and by the way, the computer doesn't actually think in terms of brains and shotguns. They're all numbers. So shotgun is 2, and feet is I guess feet is 2, shotgun is 1, and brains is 0. So the sequence is actually this sequence. So we have a function that simulates it. In real life, that could be like your robot or something. But we're going to try to learn from running this function many, many times just learn the value function v. Okay, that's what we're doing. And the algorithm looks very similar to the kinds of things we've been doing in the past. With that, yeah, question in the back or just stretching? Okay. So the first thing we're going to do is called policy evaluation, and that is where we try to evaluate the value function v. And as a reminder, v is the expected value of the total returns or the total rewards from any given state. And so we're just going to simulate it like we've been talking about this Monte Carlo stuff. We're going to simulate it many, many times, and we're going to use our Monte Carlo formulas to write it down. So I start out with v is all zeros, and it has a state, which is the number of brains and the number of shotguns. So I initialize it to zeros with this +1 thing like you guys have been seeing in the homework. The t max is the maximum number of terms I let the game go. So if it's more than 10, we have to stop. We can't let the game go forever because then the computer won't know what to do. And we start out with some policy. So here I wrote down a policy, which is a very simple policy. The policy tells you in any given state, should you roll again or not. So the policy is just one of two values, either roll or don't. Of course, you guys have seen an example now where the policy can be there. If there's many actions, it's more complicated. But here there's only two things. And I made the policy, if you have a number of brains and a number of shotguns, if the brains is less than 5, you re-roll, otherwise you stop. So that's the policy that I'm going to try to do. And we're going to try to evaluate the value function v for this policy. So how do we do it? We're going to just loop over everything. I have this array called visits, and visits keeps track of how many times did we visit each state. And here's the loop. We're going to loop over everything. This verbose tells me whether or not I should output some text as we go. So why don't we run it? Let's run it 2 times. So let's run the episode 2 times, and it should output some nice stuff for us. Oh, you know what? I probably won't because I need to run everything. Yes. Okay. Let's run everything. So I got to run runtime, run before, and then run. Okay. So here we go. So here's what happens when you run it. So it says t equals 0. You have no brains and no shotguns. We chose to re-roll. This is like the choice I gave you guys at the beginning. Before you played the game, should you re-roll again or not? We chose to re-roll. We got shotgun, brain, brain. So now we're at 2 brains and 1 shotgun. And do we choose to re-roll again or not? We chose to re-roll. We got brain, brain, brain. Oh, that's very good. We're at 5 brains and 1 shotgun. We choose to stop. So we got 5 brains at the end. And our value function gets updated. Our value function gets updated. Before the value function was all zeros. Now the value function is like this. It has a 5 here, a 5 here, and a 5 here. And why does it have a 5 there and a 5 there and a 5 there? Well, we've played through 1 time. Every single time we played, we've gotten a score of 5 starting from 0, 0. And every single time we've gone through this state of 2, 1, 2 brains and 1 shotgun, we ended up getting a reward of 5. And every single time we went through this state 5, 1, we also ended up with a reward of 5. So these are the 3 states that we visited. We were at this state, then we were at this state, then we were at that state. And in every situation, we ended up with a reward of 5. So the running average is 5 for each of those states. And did I also print out the visits? I did not. Okay, so here is episode number 1. That was episode number 0. In episode number 1, we rolled the dice, we rolled the dice, we rolled the dice, we got greedy, and we went bust. So we got shot too many times. And now the v function is also updated. You'll notice that it's down to 2.5 over here, because in one situation we ended up with 5, in another situation we ended up with 0, so the average is 2.5. There were 2 other states that were visited, but they will have 0, and since they started at 0, they're hard to see. But that's very roughly speaking what it outputs. I'll show you the code in a second, but all it is doing, it's doing the Monte Carlo average for every single state. So the value function is v of s, is the expected total reward starting from state s. And we just run through, and we keep track of, when we started a state, how many times, what's the average of all our runs so far. I'll show you the code in a second for how it works sort of under the hood. But is the gist of the output sort of making sense? Okay, let's take a look at how the code actually works, and you'll see that, stuff that we were doing before. So how does the code actually work? So for episode in range number of episodes, we're just going to repeat playing the game some number of times. Every round is called an episode. This episode visits keeps track of which states we visited in this episode. So it starts out with all zeros, and then as we go, it'll get moved up. So when we visit a state, we'll keep track of it in this thing. All right, we start at 0, 0, and then we simulate all the dice using the simulator function from before. So in practice, if this was like a robot or something, we would like run the robot for 5 minutes or something. But in this, we just call the function that gives us the thing. Okay, and then we go through the rounds, and we say, okay, we visited some state, and then we choose if we roll again, then we're going to roll again. So if we roll again, then we add on what we saw to our current state. And if we rolled again and we got too many shotguns, then we lose. But otherwise, we will loop around and do it again. On the other hand, if we chose to stop, so if the policy of the state we're at is to stop, then we just stop. And then at the very end, we calculate the reward at the end. So if we are at the end of that round, after we're done playing, if we have less shotguns than we're supposed to have, then we get the reward. Otherwise, we just get a reward of 0. So that's like a simulator sort of taking the simulation of the dice rolls and running through it and simulating what happens, applying the rules of the game. Okay, and I guess here is the exciting part. This is the Monte Carlo stuff. So we update V. How do we update V? We update it like this. So let me write this one down on the board so we can see the math. This is the kind of formula we had earlier in the previous class. So it says V of S equals V of S, whatever it was before, plus 1 over the number of visits of S plus 1 times the reward. This is the reward. I'll call this the reward for this episode minus V of S. Okay, so this is what the formula says. And by the way, it says do this formula for all S we visited. For all S. Let me write that above. For every S that was visited. So all the states that were visited, that's what this np.where does. So where we visited something this episode, we update it like this. And where for every S that was not visited, for every not visited S. So if there's a state that's not visited, then we do the other branch, which is V of S equals V of S. So we don't do anything on the other ones. That's what the final little V over here says. So if you visited it, you do this formula. Otherwise, you do that formula. So this is the update rule. And this update rule is the Monte Carlo update rule. So the state S has been visited some number of times in the past. We do 1 over that number plus 1, and then we do this shifting rule, the reward minus V. And we add it on to V of S. So this is exactly the online average formula from before. Okay. Are things set up enough that you guys recognize that this is the same as the formula earlier? So now it's written with square brackets before it was written with Greek letters. Okay. Last but not least, we add 1 to everything that it was visited. So anything we visited this time, we add 1 to visits. Otherwise, we leave it alone. So we're just updating the total number of visits in this visits variable. Okay. And that's how the code works. So very, very simple stuff. This is like whenever people have a probability problem on the internet, this is the kind of code they run. They're like, I'm just going to simulate the thing a bajillion times, and I will run it and see what it outputs. Let's do that. So if I turn verbose to false, then it will stop talking, and then we can set a large number like 10,000 as the number of episodes, and it'll run it a whole bunch of times. Let me also, I do also print out the number of visits. Okay, great. So let's run it a bunch of times, and it will tell us what's going on. I put in this little function called TQDM, which is everybody's favorite. It makes a cool bar that tells you how far you've done. So we're going up to 10,000. We've done 5,000, and it should take us another 5 or so seconds here until it finishes. Google is doing about 500 runs per second, which is very nice. Okay, here we go. We finished. So here, the first thing it outputs is our policy, and our policy was the thing I set. Roll if you have less than 5 brains. So these are all states where we roll. The columns are 0 brain, 1 brain, 2 brain, and the first 3 the first 5 are roll again. If you have, sorry, those are shotguns. The columns are shotguns. And here's what it found for the value function. So it visited the state 0, 0, 10,000 times, and then it visited all these other states some number of times. We had 1 shotgun and 0 brains 1,000 times. We had 2 shotguns and 0 brains 946 times, and so on. And we got these for our values. So we think if you start at the game and you follow this policy, you'll on average get 1 brain starting from nothing, 1.44 brains. If you're unlucky enough to get 2 shotguns right at the beginning, you're going to get only 0.18 brains. Ooh, this is nice. This worked out to 5, 6, and 7 exactly. No decimals. Does anyone have a guess for why those are exactly 5, 6, and 7? Yeah. Yeah, so the policy says if you get there, just stop rolling. And if you get there and you stop rolling, you're always going to get 5. So it's an average of a situation that is non-random. So you just get the random, the non-random amount. Ooh, this is interesting. It goes 5, 6, 7, 0. So our computer thinks that if you're in this state, you get 0 points. What's going on with that? Yeah. We never actually visited this. So remember, we initialized it to 0, and we said when you get there, update it with what you got. But our policy was set up so we never visited this state at all. And so these zeros are actually nonsense garbage that never got updated. That's why it's wrong. It's sort of right in the sense that the policy never gets there. So what is the value of being in that situation? Well, you never get there. It's a little bit like on Snakes and Ladders, we had that state that you never got to. So that kind of thing. Okay, and there are the visits. Again, yeah, you can check, make sure you're understanding it correctly. There's 0 visits to these states. And that is why the model is not knowing what's going on there. Okay, that is like the very basics of the Monte Carlo stuff applied to the V function. And this is called policy evaluation. Policy evaluation. So given a policy, I gave you the policy, we figured out how good or bad the policy is, which is a good start because you can play with it. Is it better to do it with 5 brains or 6 brains? I guess with we said roll again under 5, we got 1.44. Let's try roll again under 6 and see if it's better or worse. So I just changed the policy over here. I'll say if you're below 6, roll again. And then I run it again. We get our cool little bar. By the way, I like to do 10,000 because the square root of 10,000 is 100. And remember, the error is like 1 over the square root. So everything should be accurate to sort of within 1% if you run 10,000 simulations. Any questions or comments about how this thing is going so far? Okay, let's see. Is it better to roll under 5 or under 6? So here's the roll under 6 policy. This says at the starting state with 0, 0, you only get 1.19. So the old policy was better. We made the policy worse. And now the question for you guys, how do we find a good policy? So this is the question now. Policy improvement. We have succeeded in doing Monte Carlo policy evaluation. So evaluating how good the value function is for a given policy. But how do we go about doing Monte Carlo policy improvement? How do we use this kind of stuff to find a better policy? So like, I tried something and it got worse. I want to make it better, not worse. So this is a word cloud. Think of any general vague idea you have and put it in there. We'll go until the timer says 2 minutes, say, and then we'll pause. All right, like 30 seconds left. How would you improve the policy? Okay, we're gonna stop there. Let's see what you guys said. And we get the fun word cloud. Here we go. Ooh, okay, amazing. Let's see, what are the big words? I'm always excited for the donut. Donut, very good. Okay, well, what words we got? Policy. So some stuff about the policies. Let's figure it out. I guess I want to see the submissions. Evaluate random policies. Take the good policy and then evaluate a bunch of random policies similar to the good one and keep iterating this way. This method is called evolution. So if you have a way of sort of evaluating what's good, you just try random stuff and then you figure out which ones are good or bad. This is a totally valid way. It's extremely slow. And that's because the set of possible policies is very large. So if you're sort of exploring around in this way, it takes a long time. So this is a nice idea, and for some problems, this is the best you can do, but we want to find faster ways to do it. So great idea, we want to come up with something faster. Evaluate a policy, change it by a tiny amount, and measure if there's an improvement, so same kind of thing. What we want to do is we want to figure out what way, how could we improve it? That's what we want to do. Use Q function. This is a very, very simple idea. So far we've done V. Before we also had the Q function. So we had Q of SA, which was the expected value when you take S and action A. So that is a nice thing to try to do. Although I guess this is a little vague, because use it how? I don't know. What do I do with it? Okay. Adding parameters. Yeah, okay. So later in the course, we're going to do it with parameters. And then we're going to use the parameters along with the thing we're going to discuss now. So the parameters on their own won't solve the problem, but the parameters will work with the thing we're going to do. And we are going to use the Q function somehow. I want to see if somebody came up with how to do it. Try lots of different policies. Simulate a bunch of policies. Okay, this is nice. This is a very specific thing of what to do. If you remember, in the Bellman equation, the optimal policy is the maximum of the Q stop and the Q roll again. So what we're going to do is we're going to evaluate the Q, and then we're going to try to do this kind of maximum thing to improve the policy. So this is the right kind of thing. You'll see that it's not as easy as it sounds. Trial and error. Finite, yeah, so this is the problem with this kind of stuff. It's true there are a finite number of policies, but the space of policies is so large it would take forever to do it. Remember, for every possible state, you could either roll again or stop. So the number of policies is 2 to the power of the number of states. So in this situation, it's just like way too big. In any real life situation, the number of policies is like so big you can't be messing with this kind of stuff. It's true it's finite, but you'll never get there. Okay, change the policy slightly. Yeah, this gradient thing is what we're going to be doing like next week. So you guys have to figure out how to use the quality functions, the Q functions. Okay, let's go in the code. And so below here, I have redone the same exact code as before, but instead of doing it with V's, I did it with Q's. So instead of having one value of V, now I have 2 values of Q. I have Q state and Q roll again. And just like before, I can do everything like I did before. One important thing to notice is now the visits also depend on state and roll again. So I say, if you were at a state and you chose to stay, or if you were at a state and you chose to roll again, how many times did those things happen? So I'm kind of thinking of the states and the actions together. The state action pairs are the thing we are counting. So the thing we do Monte Carlo over, I'll say MC over, are the state action pairs. Before it was only the states, now it's the states and the actions together. And I made a policy, so same kind of policy as before. And okay, now I have the same kind of situation as before. It outputs almost the exact same kind of stuff. What is different about it? Let me get rid of this thing. We'll put that back in later. So yeah, we do exactly the exact same kind of stuff. We get the action from the policy, and the only difference is now when I update the visits, if you chose to roll again, then I update the roll again visits. And if you chose to stop, I update the stop visits. So very nice. And okay. Okay, and now I have 2 update rules, updating the state, updating the roll again. So it's all split up by what action you did. In this problem, it's very nice because there's only 2 actions. So I just have to write all the code down twice. Very simple. Okay, so if you run this right now, it does exactly the same stuff as before. It should just also tell us the, is only 1,000. Okay, okay, great. So I ran it 1,000 times, and this is exactly the same kind of thing we had before. Here's Q state. if you choose to stay, well, we never chose to stay for these states. So the visits to the stay situations has a bunch of zeros. We only chose to stay in the 5, 6, 7 range, just like before. And the Q roll again is the opposite, right? We only chose to roll again in the first 5. We never chose to roll again here. And so this is like a split in 2 version of what we did before, and here's the policy it found. Is there a question at the back? Or? Yeah.
For the first few like Q stays, it has like a 077 or like.
Yeah.
Why that was.
Yes, this is a great thing. Yes, this is 077. I'll give you a hint. It has to do with the this line over here. This is the number of times we visited the states. So first of all, the reason this is 7, we visited that state 4 times and 12 times, and every time we visited it, we got 7 points. So like the way we're doing this, we're pretending that like in the actual game, you know if you stay, you get the number of points. But we're pretending you don't know, and you're like learning. You're like, oh, I stayed and I got 7 points. In this situation, we were never there. We never visited the state of having 7 brains and 0 shotguns. And so we're like, we don't know what happens if you have 7 brains and 0 shotguns, because we never visited. That's a great question. So far all I've done is I've split up. It's exactly the same code as before, except it's split up into stays and actions. So before it was all mashed together into the V. Now it's split up by action.
I was just wondering, is there a way that you could like get the Q function from the V function instead of like from the
Yes.
equation or something, instead of just like solving directly for the Q?
Well, so in this situation, because we know the policy, if the policy is fixed,
Yeah.
then like you'll notice like the action was just a function of the state, right? So actually like s comma a, even though I split them up here, really is just s. If you know s and you know the policy pi of s, then you know the action, you know s comma a. And that's because the policy is right now is entirely static, not changing at all. But in 1 second, we're going to start messing with the policy, and then it will no longer be true. And then once we start messing with the policy, then you won't be able to get what is it? In one direction is fine. You can always get V from the Qs, right? Because V is supposed to be whichever is better. The best possible V is, so you can get the V from the Qs. You cannot get the Q directly from the V, I think. Yeah, that's true. Right, that's right. So, because the V mashes together all the possible like actions you could have taken into one, right? It sort of like deletes what action you took. And if you're doing like one action sometimes on the other action, sometimes they get mashed on top of each other, and there's no way to unmash them. Yeah, good question. So far it's exactly the same, but now we can change the policy as we go. So that's what we're going to do. Things are about to start getting messy and weird. So if you have a question, you should ask your question now. Any questions on what's going on now? So far we're just averaging stuff, but now things are going to get exciting because we're going to start doing stuff like saying, look, at the beginning of the episode, instead of just running everything, let's change the policy, right? So every time we do this, we're getting more and we're getting better estimates for Q as we go. And if we have a better estimate for Q, we can make a better policy. So we're going to change the policy. I'm going to make the policy equal to, this is what we did last time, and it worked perfectly fine. We said if rolling is better than staying, then you should roll. And so this is how I do it. If rolling is bigger than staying, then this is a true. And so the policy will be a 1, and we will roll again. If rolling is not bigger than staying, then it'll be a 0, and we will choose to stay. Right now, this is going to make trues and falses in the policy, which I guess is fine. So I'm going to run it. Does anyone have a guess of what will happen in this policy? Yeah.
It's not going to update the policy ever because we're separating them. So Q roll is always going to be yeah. Well, whenever Q stay is always Q roll is always 0 when Q stay is it, and Q stay is always 0 when Q roll is it. So it's just going to be the same policy again. Yeah.
Okay. So this is a good observation. Is that something funny is going to happen? Let's run it and see. And by the way, yeah. So when we were doing the Bellman equation before, we did this and everything was fine and it worked totally fine. You're going to see now it's going to get all screwed up. Let's see what happens. So I run it. Fortunately, I think I only did 1,000. What happened? Oh no. So it's all zeros. Q stay all zeros. Q roll all zeros. Visits roll is all zeros. We never visited any state and then chose to roll. And actually, there's one hint on what is happening here, is that the 0, 0 state of having 0 brains and 0 rolls says 1,000. So what happened in this situation, we ran it, and because we initialized everything to all zeros, right, when we started the game, we started everything at all zeros. We said the Q function just started at all zeros. Don't worry about it. We'll figure it out over time. But then when we went to update the policy, it was 0 versus 0. Is 0 greater than 0? No. So the policy says never roll, right? So by doing this, we get the never roll again policy. That's not good. And that is what happened. We never rolled again. So we were just playing the game and we're like, start the game. Okay, not rolling, done. Which was a funny joke before, but now it's a bug. How are we going to fix it? Anyone have an idea? How would you fix this bug? Yeah. At the end of the loop. Okay, that's a good idea. Let's do that. Let's see. I don't actually know what that'll do. Let's find out. At the end of the loop. So update the queues. Put it right here. Okay. Run it. Okay. Great. Look, we did 999 times we chose to stay. Rolling. We rolled. We played one round where we rolled. So we played through the first round. Where the policy was set to the policy of the roll under 5. And then after that round, I guess in that round we lost, and then it was back to all zeros, and then after that we did all staying forever. So putting it at the end of the loop didn't work. How else could we fix it? Yeah? Greater than or equal to. Okay, great. So if the problem is we're staying too much, let's give the ties to the roll. So if the computer thinks they're equal, we'll tell it to roll again. And that way we'll get some movement, you know? Let's do it. Roll again. Let's do it. 1,000. Uh-oh. Q stay. Now Q stay is all zeros. Q roll, interestingly, 0.02. We got all these visits. And the policy says true, 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 true. So now you gave the policy, you said if it's a tie, roll again. And now it thinks roll again no matter what. Now it is never staying. I think the reason, because we also moved it to the bottom of the loop, there was one round where we chose to not roll again, to stop, or something. But okay, so this doesn't work either. This has the opposite problem of, before the problem was we never chose to roll, now the problem is we never choose to stop. And both of these things are manifestations of the really difficult problem that we didn't encounter before. Before, we were checking all the possible states. But when you do Monte Carlo learning, you only check the states that your policy goes through. And this is kind of like a really serious chicken and egg problem now. Because if we want to learn about what's going on in this game, we need to visit a lot of states. And if we have a policy that is based on our current knowledge that is wrong, then we might get stuck in this kind of thing. So this is a really important problem that we didn't have before. Let me write this down on the board. So before, this was when we were doing the value iteration. Before, we would see all states, or we would update all states. We would learn about all states. Learn about all states. All states. And then our knowledge of V or Q improves as we go. And we could do this because we knew the rules of the game. So for example, in your homework assignment that is due a week from Monday, a week from yesterday, you know the rules of the game. You know, there's a 1/6 chance of busting when you roll the dice in pig. You know if you bet, you win with P-win or you lose with P-lose. And you have the knowledge of the game. And so the only thing that you don't know is you don't know the exact value of V and Q, but that's improving over time. And you can learn about all the states because you know the rules at all the states. In Monte Carlo learning, we have a really serious chicken and egg problem, which is that we can only learn about states visited under pi. And the problem is, what is pi is set by VQ. And so they affect each other, right? The policy pi that sets what we see depends on how right or wrong we are about our value functions V and Q. And if we have a bad V and Q, maybe we have a very bad policy pi that doesn't even visit the states. And right now you're seeing kind of the dopey bug version of that, where we're doing absolutely nothing. But this is the problem that will haunt you forever. in these Monte Carlo things. And we're going to learn all sorts of tricks sort of to get around this kind of stuff. So trying to solve this kind of thing, which was a problem we didn't have before, is going to be sort of a major theme of the next little bit. Okay, with only 3 minutes left, I will pause for questions. Any questions or comments about that? Yeah.
Sorry, so just before or first?
Before means like before the break.
Okay, so like value iterations?
Yes,
Okay.
exactly. So before, when we were learning where we knew the rules of the Markov chain and we were learning using the matrix or like those probabilities, now we're trying to learn in a world where we don't know the probabilities and we just have simulations. Yeah.
Is the solution to choose the wrong policy with probability?
There are many solutions, and one of them we're going to see is that you don't want to pick a policy pi that is deterministic. You want to pick a policy pi that is random so that it explores a little bit. So one solution will be use policies that we know are bad that prioritize exploring. So one solution will be emphasize exploring. And one way we can do that is we can use random policies. E.g. random policies. And so the idea is that if you're always doing the same thing, that might be the best thing to do. But when you're trying to learn about the game, always doing the same thing is going to hinder you from learning what happens in different situations. And we're going to want to sort of explore the space of possibilities enough that we don't get stuck in a loop where we end up only trying one thing over and over again. We want to try a bunch of stuff and see what's the best. So that's going to be next class. And then once we sort of nail this down, then we're going to learn how to do it with parameters as well and gradient descent and that kind of stuff, which will be very similar. Okay, we'll stop there and see you guys on Thursday. Yeah, don't forget your homework is due on the Monday coming up. That's all value iteration stuff.